like,
Following integrals.
well, yeah, there's that part of it, but the main part, I think, in terms of the value of it, is understanding like why you would set it up one way as opposed to another.
Yeah.
So that's what we're going to get. But the good thing about multiple integrals in this class is that once you get it redefined in terms of a single variable, calculator all the way. Okay, so unfortunately with triple integrals, that means that you have to do the by hand stuff twice before you can get numbers involved. If none of this sounds familiar, then don't worry about it. It's not supposed to. So the squeeze theorem is what I was hand waving about last class. Is the way it was explained to me was, right, so if you got a function up here that's got a limit, and then a function down here that's got like the same limit, all right, and then there's a function in between. If these two boundary functions have the same limit, then the one in the middle is totally going to have the same limit. All right, so.
What was that?
What minute?
Yeah. So, anyway, so but that's in essence what the squeeze theorem is telling us to do. But obviously, it's a little bit more complicated than that. I would have liked to have learned about that a little bit more when I was a student because I would have understood limits a lot better and also their importance. Didn't figure all this stuff out until I became a teacher.
I'm reading the top thing about circles and stuff. I don't think it gives two functions.
Because there is no above and below necessarily
Yeah.
in 3 dimensions, because you have left, right, forwards, backwards, kind of that way, kind of that way. So yeah, you could bound it up, down, left, right, but can you bound it in every direction? If you were to bound it in every direction, you would create a spherical region.
Yeah, but they want a circle.
We got to start somewhere. So that's the thing. We start off with a circular region and then extrude it out into 3 dimensions. All right. So the question becomes, okay, so we're being told to prove that the limit exists and specifically is equal to 0. You might try the obvious thing, plug in the zeros and call it a day. The problem is 0 over 0, unfortunately, is not equal to 0. All right. So that's not going to fly. And also, what 0 over 0 really tells us is that there is a limit. We just got to do the work to get there. All right. Now here it's telling us that it exists and is equal to 0. So at least we have a sense of what we're up against. Because, you know, like in Calc 1, if you throw it in the calculator, you'll have a sense of what the limit is supposed to be. Here, I mean, you can't put this in your calculator. So anyway, what I need is a relationship. I need a relationship that I could build to equal this ratio. All right. And so that relationship is going to be the formation of an inequality. The idea is that I want to create the boundaries that contain this function within. All right. So this is where we start. We have x squared plus y squared as a denominator. So I'm going to write a fraction of 1 over x squared plus y squared. I'm going to ignore the numerator for now. All right. Now 1 over x squared plus y squared, that's some value. I don't know what that value is, but I do know that it has to be more than or less than some other value. So what I'll do is I'll take 1 over x squared, just the 1 over x squared part of it. Now 1 over x squared is a fraction. Now if I increase the denominator of a fraction, what happens to the overall value of the fraction?
Goes to 0.
It'll go to 0 if I increase it without bounds, but generally it's going to be smaller, right? All right, the fraction would be smaller if I increase the denominator. So what I could say is that 1 over x squared plus y squared is going to be a smaller number than 1 over x squared. Because I'm dividing 1 by less, right? Try it out with something else. You know, try it out with, like 2 squared and 3 squared, and then just go with the 2 squared. You'll see. And it ends up being that I'm not lying, right? Now, if I were to create the graphs of these two functions, wherever they are in space, they would be bounded on either side by the function and its reflection. This is a true statement. Now, it may not be the most overly helpful true statement, but it is definitely true. If I plug in a number here for x and another number for y, and then test it out, let's say that I went with 1 over 2 squared plus 3 squared. This would be 1/4. Well, 1 over, that would be 1/13. 1/13 would be between 1/4 and negative 1/4. All right, so all we're doing is kind of taking into 3 space what we knew that we could do in 2 space, and that is if you have some function, let's say it's, I don't know, look at something like this. Something that's asymptotic with the x-axis. All right. If I know that it's bounded on the high side as we go out towards positive infinity by some function that we'll call f of x, then on the low side, it would also be bounded. All right, that's what we're going for, something along these lines, but we're working with surfaces here, so that's not necessarily going to translate. But what we do have is a relationship that we know is true. Right? This is something that we can verify. This number, whatever it is, makeup values for x and y, will definitely be between this number and that number. Now let's see where we can go from there. All right, so what I'm going to do is manufacture the original limit. I need an x squared y over x squared plus y squared. So I'm going to take each fraction and multiply it by x squared y. In which case I'm going to get negative y less than, I'm going to leave a little space, x squared y over x squared plus y squared less than y, leaving a little space in front of that too. All right, so I'm performing an operation on an inequality. I can multiply each part by whatever I want, divide, as long as they're real values. Add to each part, subtract from each part, all the basic operations. Take the square root of each part, right? In this case, I just chose to multiply everything by x squared y, so that the middle of this inequality will be the function that we're looking to evaluate. Right? So what I need is the limit of that. So I'm going to find the limit of each piece. So the limit as xy approaches 0, 0. That ends up being the hardest part of the process when you get the hang of this. Physically writing in limit as xy approaches 0, 0. So, what is the limit of negative y as xy approaches 0, 0?
0.
0.
So it's between 0 and 0, it has to be 0.
Exactamundo.
But this is a plane that we're referring to, right?
This is, it's a surface, not necessarily a plane. It's a funky surface.
Care if we put the equal sign under plus then?
No,
Okay.
because it's just what we're approaching. Don't actually have to get there. So it's approaching a value of 0. Therefore, the limit as xy approaches 0, 0. There's little procedural stuff that we all learned to.
A limit that equals 0 is fine, right?
Say it again?
Is a limit that equals 0 fine?
Yeah, nothing wrong with it.
I just don't remember all the rules.
It's anything over 0 that's the problem.
Anything over 0.
Right, including 0.
Oh, over.
Yeah, 0 on the bottom, you get a problem.
I was thinking like 1. I'm like, I mean like a division problem.
Yeah, yeah. So if you had 1 over 0, that would be bad. 0 over 0, definitely bad. But if you have like a clean, real number, no matter how ugly it is, it's still fine.
Still counts.
still counts. Still gets the job done. Okay. So, there's a school of thought here that says, well, who's to say that it should be less than 1 over x squared? Maybe we want it to be 1 over y squared from the boundaries. Often cases it works either way. Generally what happens is it ends up being a little easier to do it one way as opposed to the other. So I default to writing as functions of x, only because that's just where my brain goes, and probably most other people too. You spend an awful lot of time learning about functions of x, and only now are we creating functions involving y. Right? So that's not unreasonable. So default to the x's, and if you gotta go to the y's, go to the y's. Like in the next one, I mean, it's a mess. Look at this thing, it's nasty. But it's not so nasty that we can't get started on it, because what again we're looking for is a relationship. The denominator that they gave me, as ugly as it is, still a fraction. It's got to be less than something. So I'm going to write that it's less than 1 over x minus 1 squared. Okay. So again, you're dividing 1. In each case, you have a numerator of 1. Here, you're dividing 1 by more stuff. All right. 1 pizza pie, more people. Each slice is going to be smaller, right? 1 pizza pie, less people. Everybody gets more pizza. Some delicious Frank Pepe's pizza with roasted red peppers and the Pepe salad.
I got negative of pie. Nobody gets a pizza.
I love pizza. I eat pizza every day of the week.
Yeah. Some vegetarians chew my ear off because I eat meat every day.
Wait, what?
Those people like I eat vegetables every day. I told her I'm kind of the complete opposite. What is it called? Like a carnivore or whatever?
Right, you're a meatitarian.
Yeah. I told her I eat meat at least once a day. I told her like on Sunday, I'm pretty sure I eat it 3 times a day for breakfast, lunch, and dinner.
And so you caught heat about that? Like, oh, it's one of those you really shouldn't do that kind of things?
It's not good for your health or whatever. I'm like, you should get more greens in your body. I'm like,
all right. I thought it was like,
It's not good for you, though.
like, oh, you shouldn't go in.
yeah, who do you think you are eating all that meat? Like, you should do it like me, because...
Anywhere near someone like that eat enough.
Yeah.
That's how the conversation started.
The reason we're omnivores.
Yeah. Oh. There's a reason why they have the barbecue platter at Brother Jimmy's, too. So, I'm going to run through the x minus 1 squared ln of x. All that's basically saying is, what do I want in the middle? I want the given function. So, make it happen. Multiply by whatever you need to multiply, usually the numerator, in order to make that the result. So in this case, we're looking at negative ln x is less than, leave a little space. You know, you could skip the step if you want, I guess. So multiply everything through, and you're going to get the negative ln of x and the positive ln of x. And so all I just need to do is apply the limit as xy approaches 0, 0. Bane my existence. Oh, 1, 0. Thank God. Because I was about to make up some line of crap. Yeah, because fun fact, can't take a log of a negative number, and you can't take a log of 0. So if that x value was something other than 1, less than 1, we might have had a problem. So anyway, plugging in the 1 though, we get a clean 0. which is precisely what we were looking for.
Limit of 1 is 0.
Limit of 1, 0 is going to be, limit as x, y approaches 1, 0 is going to be 0. I don't know, so limit again. X over, oh my god, blah, blah, blah. If you're wondering why I'm taking great pains to write all of this stuff, even though it's like, yeah, do we really need to write it? Unfortunately, you really need to write it because a limit is a proof. It's a proof of a particular occurrence, but it is still a proof, right? So what we need to do is be rigorous and explicit in our proofs, which means that all this crap has to be there. All right, so if you're looking for a long story short on that one, that's the long and short of it. Because I've had people just like mysteriously drop, even Calc 1, just drop limit throughout the whole process. And it's like, well, the minute you drop the limit, it's not correct anymore, right? Because honestly, I don't know that it's actually ever going to get to 0. Because remember, you could be approaching a discontinuity. You could be approaching a hole in the graph. There doesn't actually have to be a point there. So if there's no point there, but you're still aiming from all directions for the same location, your limit would still exist. But if you drop the limit, you're telling me that the point exists there, right? So you're evaluating a function rather than finding the limit of the function, right? Those two things go together. They go hand in hand in order to address continuity, all right? So in the case of something like number 6, we have to figure out whether a point exists, and then on top of that, whether the limit exists. In a lot of cases, it's pretty straightforward, but there are some exceptions. Right? So the first thing we look for is discontinuity.
Does 3 space have the sort of thing with 2 space where, like, if it's rotated a certain way, it's not a function, it's an equation? I'm looking at the graph of 6.
If it's rotated,
Like, if you rotate a parabola on its side, that's no longer an equation. Or that's no longer a function, it's an equation because you have to write it with a piecewise.
yes and no. There are some circumstances, but they're very loosely defined, because generally anything in which you're getting a z value from an x and a y as independent variables, in most cases you end up with something that would be considered a 3-dimensional function, but there are exceptions. It's basically a plane instead of a vertical line. So, but we're looking. See, the thing is, in 3 space, we're actually looking for different things. So often the result of like a quadric function, for example, which is your 3-dimensional surfaces related to conics, like an ellipsoid or a parabola or things like that. Often their solutions are things that you would not quantify as functions necessarily. Right? You'd look at them and say, well, that's an ellipse. It's not a function. It fails a vertical line test. Right? The minute we switched over and started thinking of things parametrically, we opened up the door to take things that wouldn't ordinarily be considered functions and write them as functions. Because if I have something like a circle, for example, not a function, right? But if I write it as x equals cosine of theta and y equals the sine of theta, now x is a function of theta and y is a function of theta, right? So independently they become functions of another variable, right? So the way we define functions moving forward is more kind of looser of a definition, and it's words to live by, I guess. Have you other question?
Yeah. You know how you say in 2D it's f of x equals like a y. How would it be on 3D? Like what?
F of x comma y.
F of x comma y.
Yep. And that takes the place. Z takes the place of that. Like y would take the place of f of x. All right. So in this case, if I were going into Geogebra or something like that, I would write z equals, just for convenience, all of this stuff. All right. So what I need to do here is take a look at my denominator. And got this guy right here. Can't be equal to 0. In which case we get a path y equals x squared. All right. So the relationship has to be such that the x value squared becomes the y, which means that when I define my variables for the limit, I want to have whatever the y value is be the square of x. All right, so I would create parametric equations. X equals t, y equals t squared. All right. Now, any relationship here where y is equal to x squared is not going to be continuous. So I can actually make the statement for the domain that it's xy such that y cannot be equal to x squared. Which would imply that everything else would be or give us locations in which the function is continuous. The thing is, we have to prove it. That's the issue, or at least justify it with
Why are we
limits.
making our parametric equations based off of dx, the line, I guess, where it's defined to be non-continuous?
Because what I'm going to do is using limits, is I'm going to show that the limit does not exist at or involving these two parameters.
But how's that prove the limit exists everywhere else?
Well, you can only do so much. So what I'm going to do is focus on the one case that I know has to be relevant, and then go from there. Because if I've already accounted for the fact that the domain must exist under these circumstances, then really the only thing I can do is focus on the restrictions and not every other possibility. All right, so it's kind of like
With this map, all we can figure out is what it can't do.
correct. So substitution, we'd have f of t be equal to t over t squared minus t squared, which is t over 2t squared.
Would it be
No?
t squared minus t
Oh,
squared?
duh.
So
Because that's a minus sign. Thank you. All right, so if I'm looking for the limit as t approaches some constant a of f of t, what I'm going to get from it is the limit as t approaches a, some constant a, of t over 0, because that's a simplified form.
And then you just write DNA.
Right. No solution, therefore the limit does not exist. So we would say function is not continuous for y equals x squared because
when you say limit of t approaches a stands for any real number.
any real number, yeah. Because corresponding limit does not exist. All right, therefore, continuous on the interval for x, y, everything except for y equals x squared. So its continuity corresponds with its domain, which is not rare. That happens very, very frequently, but this is the process we use to justify it. Right? So we come up with the path in 2 space that corresponds to the restriction within the domain, parameterize it, because again, if you try graphing y equals x squared in 3 space, you're getting a parabola with infinite height, a sideways parabola with infinite height, right? I guess it would always be sideways because it's going to be one of these bad boys, but up and down.
That bottom part is supposed to be y does not equal x squared.
Yeah,
Oh, I missed the not equal sign. Right, so basically the red diagram here is what that path would be, but if I'm going to represent that as a single path along the curve, or the one corresponding with the function itself, I would want to parameterize it in terms of t. Right? And so that allows me to redefine my function in terms of t and see that it does not exist for any of those values in which the relationship is y equals x squared.
You couldn't just leave that as the domain that you put up originally. You still had to put in parametric equation form first.
In order to get it into a form that you could apply a limit to. Because otherwise, actually, honestly, I didn't even bother checking. Well, yeah, you would have to do something like this because you'd never be able to generalize it in this form, right? Well, not necessarily true. There's a workaround. You would have to write the limit as x, y approaches a comma a squared of the original function. Then you could plug and chug all day long, but it's not going to work out as cleanly as this.
How'd you get x equals t?
X equals t. Oh, well, I decided on a parameter for x. Whenever you're putting in a parametric form, you get to decide for one variable. This is the one I'm going to call t, and then everything else is based off of that information. So once I decided to call x t, then the relationship is that whatever x is squared becomes y. All right, so decide on one and then use that to define everything else. Yeah, this may seem like one of those things that's a little unnecessarily complicated, but it kind of drives home the concept of a limit, and so there is value to it. I know it's not the most popular type of question, but or at least if it does, we have to go through the entire process of showing that it does. But the issue here is, again, just going back to this idea, we know that the limit is 0. We don't know that it actually has a point at 0. All right, that's the concern here.
Even though it's a piecewise function, don't we?
It is, as Mr. McCallie would say. All right, number 7, a little piecewise function, but involving functions of multiple variables, which is exciting. This is what we just worked with, right? So, is it? Cool. So we have something that does not exist for us at 0.
Know that the discontinuity is at when x and y are equal to 0, 0.
You would think, well, I mean, they're forcing it here by saying it can't be equal to 0, 0, but it is possible that you could have an equal sign here and an equal sign here with a graph that naturally doesn't exist at 0, 0, where the second one fills in the gap.
So that second one's filling in the gap, but don't we know that it's discontinuous at that one point?
Right, but we don't know in what way. Like, we don't know if 0 for z fills in the gap, because if we don't actually figure out, and now this is an extension of a previous question, but if you don't actually figure out the limit as x, y approaches 0, 0,
Is equal to 0,
if you don't figure out that limit is equal to 0,
then it's not.
then that 0 might not plug in the hole. Because if the limit of this is 2, for example, all right, cool, we got an extra point at 0. Doesn't help us fill the gap. All right.
That's when we would know it's not continuous there. But if they both hit 0, then we would know it's a continuous function, and then we would state it's always continuous.
Exactly.
Okay.
So we got this from, what is it, question 5? See number 5.
No, it's 4.
See number 4.
Limit equals 0. Yeah.
All right, I went the wrong way with that. So we also know that we have a z equal to 0. All right. So this one plugs the hole from the first piece. Therefore, everywhere continuous. All right. We have a sum of squares on the bottom of the fraction, so we didn't have to evaluate any other instances in which the function might not exist. There's no radicals, so I don't have to worry about imaginary. Okay, so the only concern for this problem was the coordinate, well, the x and y coordinates of the order triple of 0, 0. Right? So it turns out that this hole is actually at the origin, is at 0, 0, 0. But you don't get that until you find the limit, right? So, you know, you look at a question like this and you see how it has the concept of a limit embedded in it, but it doesn't necessarily lead you to think that this is a squeeze theorem problem. But if you're given a problem like this on the test, you have to find the limit using the squeeze theorem of that first part, and then you could verify that the 0 does in fact plug in the gap, and then go from there. All right.
So if we did that and we didn't get that the limit of the x squared y was equal to 0, would that mean we just did it wrong, or?
No, because the question is find all points where the function is continuous. It could be everywhere except for 0, 0.
Oh, okay.
Yeah. Number 8, just an expansion on some Calc 1 ideas, nothing too crazy. Continuity of combinations of functions. Some are difference of continuous functions are continuous. So if I, sine the sine function and x squared, for example, in 2 space, they're continuous functions everywhere, both of them. If I add them together, the result will also be continuous. All right, if I multiply them together, it'll be continuous. If I divide them, except for where it would be undefined, it would be continuous. All right, so shouldn't be a bullet point. Typo bonus for someone. There should not be here. There should be like. Actually, I don't even know why I have that line there. Must have copied that from a book or something at some point. One has to be a bit careful.
So some does. It's pretty sure word for word from textbook. Like he says stuff he doesn't know what it means sometimes.
Yeah. All right, anyway. We have composition of functions. Suppose that f of xy is continuous at ab and g of x is continuous at ab. Then we can assume that the composition would be continuous at ab. Right? So, but what does that mean? Practically speaking, it means that you got a lot more stuff to worry about for a question like this than you would for a function of maybe a linear variable or even a function of just x. Right? So first I have to account for this. Right? So ln of x plus y itself, that whole shebang, has to be greater than 0. All right, because you can't take the log of a negative number, and you can't take log of 0. All right, so whatever the result of the natural log of x plus y is, that itself has to be bigger than 0. All right, so what I'd like to do is get a clean relationship out of this. So I'll rewrite it as the log base e of x plus y greater than 0. Convert e to the 0th Whoa, I just had a moment. I'll get the x plus y
that's the class.
Yeah, time to go. Thwarted by an inequality.
Well, if you're inverting an operation, yeah.
Yeah, right? That's what I was thinking.
Well, think of it like you have to draw your e to the other side.
Well, yeah, that's what I was saying. Like in the circular motion, my perspective is now it's e to the 0 looking that way. But it's been a while. That's
It
crazy.
hasn't really changed anything. It's still.
Well, I was just figuring worst case scenario, I would test it with a value in a second. If it came up with something like absurd, I would change it. So, well, e to the 0th is 1. Yeah, right?
Mm-hmm.
Well, can't they?
Yeah, x plus y has to be more than 1 under this context. Well, it can't be less than 1, can it? Yes, it can. Well, it can't be infinitely less than 1. So a less than symbol here makes more sense than the greater than symbol.
Can it be? Oh no, because then you would get the natural line too.
Right. Yeah, so x plus y has to be greater than 1 is what I'm going with. So y would be negative x plus 1 equal greater than. Yeah, because that would give us our benchmark. If I replaced the negative x plus 1, if I replace the y with a negative x plus 1, this becomes a 1, which is our boundary, really. I mean, based off of reasonable logic, it looks like. Anyway, the x plus y itself has to also be greater than 0, so I can make a note of that as a separate thing. So just focusing on the innermost function. So I looked at the natural log of x plus y and how that had to be greater than 0. Now I'm going to kind of bring it in a little bit further, right? So, say it again?
Isn't it already outside? Like, that's too small. Like, it's smaller than what we've already defined as parts of our domain.
Right. So what we're going to do is take, we like those logic symbols, y greater than x, negative x plus 1, and y greater than negative x. So, exactly. So, therefore, y has to be greater than negative x plus 1.
The y is greater than minus x, but this is irrelevant, right?
Right, because that's covered in this one.
Okay.
Or at least the relevant parts, because if it has to be more than this one and also more than that, we're looking for the overlap. All right, you can create a graph out of it. I'll just do that real quick.
But I was thinking, if you plug in the y for that ln, you can end up with an ln is equal to, I'm sorry, the ln of 0.
If I plug in
Y for the y at the original equation, you're going to end up with an ln of 1. ln of 1 is 0, so then the ln of 0 doesn't exist.
right, which is why we have to be greater than. So I could plug this in, but I actually need to have a y value more than that. So if I were to have it as, like, let's say negative x plus 1.01, you know, so anything as long as it's more than that particular value. Here's negative x. If we're going to have a region that's greater than the first one, or the lower of the two functions, while also being greater than the higher of the two functions, the overlap would be a little darker. The region above y equals negative x plus 1. Right? That's the part of it that's actually over. Oh, I overdid it with my My little red lines there. Got a little too ambitious.
So it's the red line, correct? That's what
It's the overlapping between the red and the purple. But that corresponds to this relation here. All right. So continuous for values that satisfy this relation. So continuous for x, y such that y has to be negative x plus 1. For these kind of problems, we don't bother proving it with a limit because it's too much of a nightmare. Once you get inequalities involved, it changes everything. It changes the complexity of it anyway. So partial derivatives, the idea behind them is that we're essentially holding one variable constant while we differentiate the other variable. Right? The idea behind that, I mean, you have all this funny notation here. I'll get into that in a little bit, but the idea behind that is that I talk about things like gradient, slope in 3 dimensions. But if we're talking about approaching a point along a path, like if you have an entire surface, you kind of need to have a place to start and some parameters in which to focus. So the question becomes, well, do I just go at it from all directions? Is that even possible? Or do I narrow down a parameter and just focus on each parameter one at a time? So in the case of finding the partial with respect to x, what that's doing is telling me that I'm just thinking of my equation as a function of x, where all y's can be thought of as constants. Right? So I'm holding y as constant, right? And it can be a particular constant. So it's like the idea of a contour plot, but imagine you're holding y constant instead of z. All right? It's basically saying, all right, I'm going to focus in on a single y value. Let's say y equals 2. Now let's see what's happening to x, the relationship between x and z, if I'm holding y to be constant at 2. Right? Then we may say, well, let's do it at 3, let's do it at 5, let's do it at 10. Let's maybe try some negative numbers in there. These are some ways in which you can kind of limit things, because I mean I often go back to statistics and I say that like if you're running an experiment, for example, do you want to have a single explanatory variable and a single response variable, one input, one output, right? Ideally. Sometimes you'll have one input and multiple levels of an output. And sometimes you're stuck. You just have 2 outputs, 3 outputs, 10 outputs, whatever. But if you can trim it down, if you can narrow it down so that you have a single explanatory, so a single input and a single output variable, then you can start to draw some conclusions, right? So what we do here is we treat one variable as just that, a variable, and the other variable we treat as a constant, right? And then take the derivative the way you normally would, right? Except instead of looking at something like yx, you would look at that previously as a product rule situation with implicit differentiation. Now it's just going to be, the derivative of yx. Well, what's the derivative of 2x? That was kind of a question. The derivative of 2x with respect to x? 2. So what would be the derivative of yx if y is treated as a constant? Just y, right? So with that in mind, you're taking things that could be complicated product rule situations, and maybe they're just simple power rule. Maybe you have something like secant squared x times y, but you're taking the derivative with respect to y, meaning y is the variable. So what does that secant squared x become?
Just a constant.
It's a constant multiple. So you don't really have to do anything with it.
Just secant x.
It's just secant squared x. That would be your derivative, right? So it can be very, very easy as long as you kind of allow that to happen, all right? Now so all of this, that was really addressing everything I just said. All right. We have the funky D notation here. We generally say this as the partial of f with respect to x. And so you would have a partial of z with respect to x, partial of f with respect to y. The only reason we say that is because you can take a derivative of a function of two variables, so not treating one as a constant. That would imply implicit differentiation. And if that's the case, it wouldn't be a partial derivative. So if I say dy dx, that means something different. So we need to be able to distinguish one form from the other. Right? So yeah, I can't do this to you today. The limit definition, we'll come back to this next class after the test. We'll move on to number 2 because the limit definition of a derivative is just really, it's a concept that's important, but sometimes it could be perceived as if it's only there to be a form of torture, right? So, but we'll do that one on Tuesday next week. For now, we'll just get into the idea of finding a partial. All right, so what I'm looking for here, partial f with respect to x. I'm going to look at it a term at a time. And blue. Oh, I had blue.
So is that similar to the backwards 6?
Yeah, it's supposed to be like a really cool looking D, but kind of like a backwards 6. Yeah. I don't know. I can never make them look good. As long as you don't make a regular D, you're going to be all right. All right. It's supposed to be a delta, but
Just slumped over delta.
yeah. But just don't make a regular D because we're still going to be working with derivative, like regular derivatives, the functions of single variable derivatives. So if you write df dx, you're wrong. Right? Everything after that could be done beautifully, but you would be incorrect. Right? So what this is telling me is that the only variable in the problem is x. So everything else is a coefficient. So what's the derivative of 3x squared?
6x.
6x. What's the derivative of 4y squared? 0.
I'm sorry, 0.
What about negative 2x squared y?
Minus 4yx.
4yx.
4yx or 4y? Matter?
It matters not.
Alright.
7xy squared becomes
7y squared.
7y squared. And the minus 9 becomes 0. It was nice. It was nice. Yeah, the one thing you got to be careful about when it comes to this, I mean, we'll get into some more extended versions of this, but the idea that, well, maybe not an idea, but I see it all the time on a test. Start off taking the derivative with respect to x, then all of a sudden you get to this and you just can't stop yourself. This becomes 8y. And then that, maybe you go back to the x, you remember it here, but so you kind of bounce back and forth between derivative with respect to x and derivative with respect to y, and you never quite get it right in either way. Right? So you just got to be careful and constantly remind yourself what it is you're taking the derivative with respect to. All right? So in this case, in number 3, we're taking the derivative with respect to y. So partial of f with respect to y. I got this guy, and then this one, which is a little bit more interesting. So with respect to y, what would be the derivative of cosine x sine y?
Cosine x cosine y.
Cosine x cosine y. All right. It's an important thing to keep in mind again. Even a cosine of x can be treated as a multiplier, a constant multiple. Right? So that's just like a 2, for example. If this were 2 sine y, your derivative would be 2 cosine y. Well, it's not a 2, it's a cosine x. So cosine x cosine y. Right? Now for the next piece, you have to know how to find the derivative of an exponential e. So e to the xy, but then also multiplied by the derivative of the exponent, which would just be an x. So I'm going to clean it up ever so slightly here. Now, when you take a second derivative, and I'll get to this in more detail in a minute, it begs the question, am I taking the second derivative with respect to x or y? It depends. We call them second order partials, and so they can go either way. And under some circumstances, they can be equal to one another, right? But if I were to, looking at this, you might look at this as a disaster. You say, oh, this is going to be terrible if I have to take a derivative again. But then consider again that you're taking the derivative potentially with respect to y. If that's the case, then x is a constant multiple of e to the xy. Now, if I have to take the derivative of this with respect to x, that's a different story. Because each part of the product, each factor of the product has an x in it, you would have to use the product rule in that case. All right? So you're not off the hook with the, I'll call them the more advanced differentiation techniques. But in the grand scheme of things, if the worst that you're going to get is maybe some product rule where before you were getting power rule, that's you're not going to lose sleep over that. All right. So yeah, so we'll do number 1 next time. So the higher order partials are where we're going to finish tonight, and then after that, I'll leave you some time if you want to ask questions and stuff. So partial derivative with respect to x. Well, if you already started off taking a partial with respect to x, and you take it a second time, this is what our notation would emerge as. So it would be delta squared f of delta x squared, which is basically the same notation as Calc 1 second derivatives, except deltas instead of d's. But the nicer way of representing it would be using the subscripts because it just involves writing less stuff. All right. So for the second order partial with respect to x, meaning you took the first derivative with respect to x, and then you took the second derivative with respect to x, this would be your notation. They say it's the alternate notation. That's my preferred notation. All right. You might have taken the first derivative with respect to y, and then the second derivative with respect to y. If that's the case, your notation would be f sub yy. It's the mixed second order partials where things start getting a little bit more, I'd say, precise, because how you write it as a subscript should be consistent with how you took the second derivative. All right? So if I did my second order partial with respect to y, after taking the first order partial with respect to x, it should be x comma y. I'm sorry, f sub xy. Right? If I write it the other way around, then I'm indicating the improper order, and that's not. It wouldn't be consistent with what I did, and therefore wouldn't be correct. All right. So how do we do it? Well, it's not hard. Right? Can be tedious, but this is skill building at this point. So we're not at the part where we're just kind of like attacking a problem for what we need it for. Here we're just practicing all different ways in which you could get a second order partial. All right, so the first thing I would do is find my first order partials. So I can note it as f sub x. Instead of writing delta f over delta x, do it this way. We already figured this one out, right? It was 6x. Then what do we get? Minus 4xy?
Respect to x
Yeah,
is
minus
6x.
4xy.
Minus
0 minus 4xy plus 7y squared minus 0.
minus squared minus. Okay, so simplified form would look like this. So I need my second order partials. One would be f of, let me do that in red, f of xy, f sub xy.
Wait, I'm sorry, it says compute all four.
All four.
So isn't it, XX? Okay.
Yeah, we're going to do them all. We'll do them one at a time, though. Derivative of 6x with respect to y.
Oh. 0.
0. Derivative of negative 4xy with respect to y.
Negative 4x.
Negative 4x. And then derivative 14y. So we can clean it up and write it as, well, I'll write it as 14y minus 4x. So I need my second order partial with respect to x. All right. So sometimes easier, sometimes not. Derivative of 6x with respect to x. Exactly. Negative 4xy with respect to x.
Minus 4y.
And then
That's it.
0, right? So that takes care of that. So now I need f sub y going back to the original. All right. So still not too bad because it's all polynomial based. You know, you have some proportional relationships here, but that's, you know, it doesn't make it any more difficult. So with respect to y, the 3x squared is going to 0. What's 4y squared going to?
8y
8y. Negative 2x squared y.
minus 2x squared
7xy squared.
plus 14x y.
14xy. All right. So from that, I'm going to snag my, we'll draw a little line here, my mixed partial, yx. I like to do that. I like to do my mixed first. I sometimes bounce back and forth, but I like, there's a little payoff when you do your mixed partials. So anyway, if I take the derivative of 8y, what do I get? 0, because we're going with respect to x. Negative 2x squared
Minus 4x.
negative 4x
Plus 14.
plus 14y. That's my payoff. That's the same as saying 14y minus 4x. So the big question would be, are my mixed second order partials always going to be equal to one another? No. But most of the time they will be. The thing is, if your original function is continuous, then your second order partials will always be equal. All right, so why do we talk about continuity? Well, for situations like this, I mean, at least, I mean, I'm not gonna BS you here. You don't need to prove that that a limit exists. You don't have to prove continuity in order to have a sense of continuity. But what I want to have happen is for you to be able to look at an equation and say, all right, that's continuous everywhere. How do I know? I don't see a denominator. I don't see a radical. It's not a funky piecewise function. So it's continuous. My second order partials are going to be equal. All right?
Is that always the case?
Always. So how does that benefit us? If I say find the second order partial derivatives for a function, you don't have to do it both ways. You don't have to worry about there being a lack of congruence. The idea is if you know it's continuous, do it the one way, whichever way you perceive to be easier, and then that's your second order partial, right? Second order mixed partial. We still have to figure out f sub yy. So 8 plus 14x.
Yes.
So computing second order partial derivatives is to determine continuity?
No. If the original function is continuous, then the second order partials will be equal to one another. A byproduct of that is that you could use second order partials to verify continuity, but it won't prove it. All right. Sorry, let me just check. All right, so we figured out one of the partials here on the previous page. kind of regret not stacking them up differently, but whatever.
It was cosine x, cosine y, minus x of e to the power of xy.
Minus x e to the xy.
Yep.
And so the other one, when we do it with respect to x, it's going to be what, negative sine x sine y. Then pretty much the same thing, but with y's. So it would be y e to the xy.
Yeah.
Draw a little purple line here. All right, so I'll do my mixed. I like the mixed. Hey, you do it any order you want. This is the way I like to do it. I like to mix it up. You know, so I'm doing this with respect to y, so I'm taking the derivative of the sine of y, which is going to become cosine of y. So negative sine x cosine y. Now, because we're taking the derivative with respect to y, that's great news, because this y is a coefficient of e to the xy. And e to the xy, we already figured out the derivative with respect to y. That was negative x e to the xy. So we're looking at negative xy e to the xy. So I'm just taking advantage of a prior answer, all right? Because we already figured out the derivative of e to the xy with respect to y, and that gave us this. We're just doing the same thing with a coefficient of y associated with it.
But I thought-
by y, shouldn't we actually be using the product rule?
I was gonna say, because isn't y supposed to be the variable here? So
Then we
take-
have to multiply by the derivative of the exponent.
Isn't it supposed
No,
to
the
be?
product rule is y times e to the x.
First we take y
But
times
y
the derivative of e to the xy, then we take e to the xy.
Right, so
times the
then
derivative of y.
plus e to the xy?
Yeah.
Yeah.
Right.
And now is the whole thing in parentheses? Because it's minus
Yeah.
that, or yeah.
Beefy. So let's clean that up a little. So that would be, just double checking. I just, negative xy. So then I want to, if I factor, this is, yeah, I'm just pulling, yeah, so xy minus 1, or plus 1. Yeah, because the negative was already on the outside, right?
X squared minus
It's minus 1.
Are you sure?
No.
No,
No, it's plus one.
it's plus, yeah.
Yeah, because all I'm doing is taking the e to the
Yeah.
xy out. But that's why I was
Yeah.
pausing the way I was, because I was like, wait a minute. Yeah, the negative was already on the outside. I wasn't removing that. All right, so then we need f of xx. But, you know what? I'm going to live with the poor quality x's there. So taking the derivative of the f sub x with respect to x. So the negative sine y are going to stay put. Sine x becomes cosine x. So negative cosine x cosine y. Because all I'm doing is keeping I'm changing this to cosine, and then everything else is a constant multiple around it.
So that's sine.
Oh, so it's sine y. Thank you. Oh, I was looking at this. That's bad news. Very easy to get crossed up here. All right, so now for the other guy, we want to take the derivative with respect to x. right, which means that the y is a coefficient now. That's what I was thinking of in the last one.
Y squared e to the xy.
Minus
Minus
y squared e to the xy. All right. So one last thing to do, because we learned in the last one what the relationship was with second order partials.
So we just copy it over.
Not even. Just kind of do what I'm doing here. Say they're equal because it's everywhere continuous. Generally with better handwriting than that, but and you may not get there right away because, especially when we're working with trig functions, these aren't bad, but I've seen some where after you do the second order partial, mixed partials, you get two things that are completely different. You're like, no way these are equal. Everything's falling apart. And it turns out you're just a couple of trig substitutions away from, or identity substitutions away from one being equal to the other. So you got to be careful about that. But in terms of value, they will be equivalent. Okay, so I just need yy.
It's the same thing except x squared.
Same thing except x squared?
Yeah.
Yeah. So it's negative sine, cosine.
Oh, negative
cosine.
sine.
It's the same thing. I just switched the order, sorry.
It's negative cosine x sine y minus x squared e x to the y. Unless I did it wrong.
No, I got the same answer. I did sine y at cosine x.
Oh, got you. Well, I was just going to write cosine x, cosine y, so I don't even know what the hell that was. So anyway, yeah. So that's really all there is to it. I mean, you can have third and fourth derivatives and things like that, but that's something for you to practice on your own for another day. But really, I mean, what's the third derivative except taking the derivative again, except you're adding more degrees, you're adding more work. So
So we get like an fx1.